Good morning, everyone. Good afternoon over where you are. And thank you very much for inviting me to speak. And I'm sorry it couldn't be in person, but I'm glad that River Lane made this happen remotely. So I'm going to talk about two aspects of quantum algorithm design, which are relatively new, I think. One is using quantum control to make explicit some algorithms which don't have explicit constructions. And secondly, and also to help with design of a robust algorithm. And secondly, the second application is using measurement. And this is really a discussion of near-term algorithms on near-term devices, sort of hybrid quantum classical algorithms, and how we have a trade-off there between coherence time, and measurement cost. So it's basically these two topics here, the optimal control. So I'll show in the first half that optimal control can find explicit solutions for sequences of quantum gates. That's been well known for a long time in control theory. But now we're going to apply this to quantum algorithms design. And the second half will be discussing the trade-off between maintaining coherence and repetition of quantum measurements in hybrid quantum classical algorithms. And I'll particularly focus there on the variational quantum eigensolver. And so, but our sort of higher level question is, how can we most effectively use these tools of control and measurement and design of measurements to construct quantum algorithms for specific tasks? So firstly, let me just get this. Quantum optimal control for algorithm design. So the first example I'm going to look at is the QAOA optimization algorithm. And we're going to use robust quantum control to design a QAOA, which performs very well in the presence of uncertainties due, in the particular instance I'll show you, the uncertainties are due to uncertainties in the parameters. And that's work with a joint student with Lin Lin in Math Department at Berkeley and Robert Kosut at SC Solutions. The second project I'll tell you about there is optimizing the phase factors in quantum signal processing. And here we are, this is really a case where we're making the algorithm explicit. So let me start with robust QAOA. Why is it not? Okay, so QAOA, summarized here, is the alternation of two Hamiltonians, HA and HB, for different amounts of times or action here, theta A and theta B, for variable depth, repetition. And this is a variational algorithm developed by Fahy and co-workers in 2014. It can be viewed as a hybrid quantum classical algorithm, or if you had an optimization, a quantum optimization algorithm, you could make it fully quantum, but it's usually implemented and discussed today in terms of a hybrid quantum classical, where one makes a quantum ansatz for this repetition of HA and HB, and then optimizes this classically, where some objective function to be optimized. Usually in the beginning, it was always the energy, but we've also used it now for the fidelity for state transfer. So our basic question is, how does this perform in the presence of noise? What I'll show you today is the performance in the presence of Hamiltonian uncertainty. Environmental noise is, of course, a very important thing to look at, and that's work and that is underway, but I will just show you the initial results for Hamiltonian uncertainty today. So we're going to use QAOA to enable state transfer between some initial state and some desired target state here. And so our cost function here will simply be the fidelity for that state transfer. And then we have a Hamiltonian control parameter set theta and uncertainties in those parameters, little delta. So these control parameters are a convex set, but the fidelity is not necessarily convex on theta for all values of the uncertainty. So what we want to do is to maximize the worst case fidelity within the feasible parameter set theta, where the control parameters are elements of capital theta, and over the entire uncertainty region, capital delta, which describes the range of uncertainties in the parameters. So this is the minimax optimization, which can be solved by sequential convex programming, SCP. And so we've applied this approach to a couple of examples, which I'll show you. One is a simple one is for a single qubit, which just illustrates the method. So if we have a single qubit, and it's the ground state of sigma z plus minus sigma z plus 2 sigma x here, and we want to transfer it to the ground state of the Hamiltonian, which just has the sign of the x transverse field term flipped. Then we can do this with a target Hamiltonian HA and the mixing Hamiltonian HB, using the language of QAOA, with our reference values of set to be 4 and minus 4. And then there are uncertainties in these parameters omega A and omega B, which describe the strength of the transverse field. And these parameters, these uncertainties, are elements of this uncertainty set capital delta. So it's known that for QAOA, the optimal procedure is essentially a bang-bang control sequence. And so we're using similarly bang-bang, we're just alternating the values of HA and HB between with magnitudes plus and minus 1 between these variable limits. So here are some results showing the worst case fidelity as a function of the depth P of the QA-OA repetition here on the left. And we see that and then the blue result is what's usually obtained, which is putting the Hamiltonian without any uncertainty. And the yellow, green, and red show the performance in the presence of uncertainty regions of the parameters of the transverse field. And as the region increases, you see the performance, so we've got the red one has the largest uncertainty region, and the performance decreases. But eventually, for large enough depths, they all basically give essentially unit within multiple nines, they give essentially unit worst case fidelity. And so this is actually showing on a logarithmic scale, how the infidelity changes with depth. And what's interesting here is, what the goal of this is to understand the role of the uncertainty in the parameters. And so on the right, you see, so my annotation is gone, my spotlight. Yeah. So on the right, you see the uncertainty plots over the parameters omega A and omega B. And we see that they have certain highlighted values, but there's generally good performance over the entire parameter regime. So this is a fidelity landscape as a function of those Hamiltonian parameters. I'm having a problem going to the next slide. Maybe I'll stop this and then go. Okay, so sorry about that. Something didn't work. So now the second example is a multi-qubit example. So it's still state transfer. We're looking at multi-qubit state transfer across a one-dimensional chain. This is like the XY model here, excitation in that model. But now we add in the center a defect, and this center connects 3 sites. And there's a parameter amplitude delta, little delta, quantifying the magnitude of the defect. And so again, we can map this to a QAOA problem and optimize. And if the task is to transfer the excitation from one end of the chain, here to the other, then we optimize the fidelity for this. And if I annotate again with my spotlight, yep, here. So we're optimizing this transfer excitation. It appears to be incompatible with, okay, so I will just use the cursor because it seems to be incompatible with the highlight. And so in this example, we we analyzed in more detail the robustness, and we see here, firstly, I mean, at the top, you see this typical bang bang pulses, and from anyone doing quantum control knows you don't learn anything really essentially from one particular pulse sequence in the optimal set or in the near optimal set. They're all very, very different. But now if we look at the infidelity as a function of the uncertainty little delta, we see that we have if there's no uncertainty, we have a very sharp peak of the infidelity at zero uncertainty. And if we have less robustness, and that the peak is much narrower. Oh, sorry, this is actually the fidelity, the negative log of the infidelity. So, and we have greater robustness, a broad peak, and lower maximal fidelity as the interval, capital delta, of the uncertainty increases. So if our interval of the uncertainty is narrow, we have a higher fidelity, the blue line, whereas if the interval is broader, greater breadth of uncertainty, we then have a lower maximum and a broader distribution. And then we see that in general, the average fidelity obtained from these results does indeed perform better than the worst case as we expect. We can also use this technique to look at robustness with respect to the uncertainty of the initial state. For instance, in this state transfer example, the initial state is not localized on the state 1, but instead has some components on state 2 and states on site 2 and site 3. Then our uncertainty is now a 2-parameter uncertainty, and assuming the control Hamiltonians are perfect, we then maximize the fidelity over the uncertainty region of the initial state. So now the uncertainty only comes from the location of the initial state, and we see very similar behavior, namely that despite the uncertainty in the initial state, we can achieve, with sufficient depths of circuit, we can achieve close to unit fidelity. And in general, the SCP, we've also compared this approach using sequential convex programming to other optimization approach, and particularly the commonly used grape variants, and the SCP is certainly more efficient and more accurate. So to summarize, what we've seen is that open loop optimal control can provide robustness with respect to the Hamiltonian and the QAOA parameters, and also with respect to initial conditions and state transfer problems. So going forward, the next question is, how do we build in robustness with respect to environmental interactions? We're currently extending this to open quantum systems. So that's work in progress now. Okay, so now let me change gears a little bit to consider using control for optimal quantum algorithm design with making an algorithm, which is a quantum signal processing algorithm, making it explicit for a specific task. And I'll explain what that means in a minute. So quantum signal processing is very closely related to QAOA. So QAOA starts from this alternation of Hamiltonians on the top to give a unitary, which is defined by some parameter theta. Quantum signal processing is normally written in this form. It's a unitary as a function of some phasor angle phi. It's a unitary which has the form of products of phases e to the I phi, phases phi j times sigma z, times e to the I alpha sigma x. And in quantum signal processing, we'll have these phases with pj's, but the other term in sigma x will be fixed, and in fact will be replaced by a more general operator. So given that similar structure, we can see that there's a relationship between QAO and the more complicated quantum signal processing. So quantum signal processing was first developed by Lau and Chang in 2016. And the goal of this is to find a unitary which generates the action of a general matrix function f, A, on the matrix A, to find that action on a quantum state. And the statement is that the f of A is the real part of the upper left of the block form, the block encoded form of a unitary operator U of phi. So here A is a n qubit non-unitary operator, and U is an n plus m qubit unitary operator. So the tool here is that one adds ancillas, m ancillas in particular, to the dimension of the matrix A that we wish to make functions of. And then one constructs this, the task is to construct this unitary operator U of phi, where phi is a vector of phases varying from 0 to p. And the explicit solution for these phases is very, very challenging. So what I'm going to show you now is a brief summary of what quantum signal processing is, and then I'm going to focus on finding the phases which define the solution to a quantum signal processing, which is our contribution, where we've been using optimal control to find those phases. Okay, so what is quantum signal processing? So the goal is to act with a general, non-unitary matrix function f of A on a quantum state. And there's several algorithms, several approaches to doing this. The first ones were essentially algorithms based on phase estimation, which included HHL, which is the linear solver. And that was a very important algorithm. More recently, we have development with the linear combination of unitaries, which requires a number of ancillar bits, log L ancillar bits to add unitary segments, and uses ideas from quantum walks. And now there's quantum signal processing in addition, which provides a direct way to implement matrix functions. And one of the advantages of it is that it requires smaller number of ancillar qubits than linear combination of unitaries and related ideas. The smaller number is obtained by interleaving the quantum walk operators and reflection operators. And essentially the two operators, that this is the part which really relates to QAOA, which is the interleaving of two different types of operators. Quantum signal processing also has a nice feature that it's an intrinsic representation of matrix functions, and it doesn't rely on any specific form of the expansion, as you'll see shortly. So what goes into quantum signal processing? Well, we have to first of all encode the non-unitary, non-qubit Hermitian matrix A. That's relatively easy to do as part of an m plus n qubit unitary matrix. So we put A into the top upper left corner of our larger matrix, which is n plus m, deriving from m plus n qubits. So that's U of A. And then A will be then the block, the upper left block of that, written in this form. And so we have now a circuit we can make a circuit for the action of A on psi by constructing the unitary A here, which goes in the side here. So then we undertake what's called qubitization, which is a procedure whereby we encode eigenvalue information into phases, and that proceeds in two steps. We have a reflection operator U pi here, and we have our U of A, which is from the block encoding from the previous slide. These are both unitary and Hermitian, and then due to Jordan's lemma, we can show that that implies that the Hilbert space of the n plus m dimensional system is can be decomposed into two-dimensional and one-dimensional spaces, which are invariant under the action of u pi and ua. So then if we make this operator omega, which is called the iterate operator, this will encode eigenvalue information of A into two branches, each characterized by a phase, theta j, plus or minus theta j. And the statement of the quantum signal processing theory is that with a suitable choice of phase factors, the unitary u phi written here can implement the function f of a. So this is the unitary u phi of the quantum signal processing theory. So it has, as you see here, a product of operators capital omega, which is the iterate operator, acting together with these exponential of I phi j tilde times the reflection operator here. So you see you have here this repetition of the phi j's and the operator u, the reflection operator, and with the iterate operator here. So that's a resemblance with QAOA. And here is a circuit, schematic circuit, which shows how you would generate f of a explicitly if you knew what these phase factors, the phi n's, are. And these phis here are related by some constants to these phi tildes here. So I haven't told you anything really about how this theory is constructed. This is the work of Lo and Chuang and Guillen, Weaver, and others over the last few years. It's a very beautiful theory. The starting point of our work is to determine what these phases actually are. Because the original theory is an existence theory and is not constructive. So the important part of the theory is, or an important part of the theory is this following theorem from Lo and Chuang and Guillen and co-workers, which says that for any polynomial, complex polynomial, and a positive integer n, satisfying these conditions, that this set of phase factors does exist. Okay, so these are the phase factors where the iterate is now labeled W here. And so the claim is that this unitary signal processing operator can be written as this block diagonal, block matrix in terms of polynomials P and Q. And the real part of the polynomial P, which is in the top left block, is the function f of x that we're seeking. So this means that the QSP problem, and this is a 2x2 problem now. So this means that the QSP problem is reduced to finding the vector phi with phases little phis, which solves the corresponding SU2 approximation problem. And if you have a complex valued function, then it's easy to implement QSP for this as well, because you just decompose the generic complex valued function into real valued functions with definite parity, so that then you can implement each of these four terms separately according to the previous theorem, and then combine them by linear combination of unitaries. So there's a theorem here that shows you can do this. So there are very many QSP problems of interest. For instance, the function f of x could be the exponential of I tau times x. So it could, and where x could be the Hamiltonian. So that would be relevance to quantum simulation. Or f of x could simply be 1 over x, which is relevance to linear algebra. That would give you matrix inversion. Or one can have eigenvalue filtering and so on. So the real problem with the application of this technique, and which the reason it hasn't been used very much in practice to date, is that it's very hard to find a set of phase factors that encodes the real valued function with definite parity. So the task is to find these phase factors, which the vector form the vector capital Phi. And there have been several ways to propose to address this, in particular from Gillian and co-workers and Ha. And I'll show you the results from these. The difficulty is that they need very high precision arithmetic, and there's numerical errors in root finding techniques that are used. So there's a lot of error propagation that arises when this is solved by a reduction procedure. So the alternative that we have been developing is to do minimization in terms of a loss function. And in particular, we're simply minimizing the distance between the function that we obtain with the function parameterized by the phases and the f of x that we want. So the advantage of this is that only matrix multiplications are involved, and these are numerical stable. And secondly, we use partial information about the QSP unitary, but we don't need a root finding step. And then we don't require, as a result, we don't require large floating bit arithmetic. So here's an example, Hamiltonian simulation problem. So here one has, so our function x is up here in the exponent, and x would be eventually the Hamiltonian matrix of a system. And we want to time propagate, find the time evolution operator for that Hamiltonian, which is of this form. And so we make an expansion in Jacobi angular polynomials. And this is a problem originally posed by Low and Chuang in their first paper, which has now been reprinted in a larger version in Quantum in 2019. So we carried out this optimization procedure, which is actually, we use standard optimization methods. And we're comparing here with the two approaches from GSLW and Ha, which use this reduction method and very high. On the right, you see actually it's not a plot that one shows very often, but we're showing here the number of bits needed to find the solutions as a function of tau. Tau is the time for the particular time step, and the order of the polynomials which you need to use is given up here. So we're using very high order polynomials such that this is covered on my slide. So we need very high order polynomials of order n as you go to larger times tau. And we're choosing this particular parameterization here, so which ensures that the error is less than 10 to the minus 14 in the evolution action of the evolution operator. Okay, so let me discuss first of all what's here on the right. What's here on the right shows the number of bits required to evaluate the phase factors for these high order. So as tau increases here, basically the relationship up here tells you that the order of the polynomial that you're using to do the time propagation is increasing linearly with tau, maximum tau. And in our approach here, you see that we're not changing the number of bits needed to compute this. That's because we're using always double precision. So our number of operations, so the number of bits remains constant. Whereas GSLW and Ha have to use variable precision arithmetic, and their number of bits increases substantially, especially for Ha's approach, whereas as the order of the polynomial increases. The accuracy is shown, okay, so the accuracy is in all cases of order 10 to the minus 14 in the loss function, okay. And what we show on the left is the CPU time needed to get to that accuracy for the three different approaches for a given value of tau, corresponding to a given order of polynomial. And we see that GSLW is here, which uses a reduction method. They basically can get up to a few hundred, but then their method becomes unstable and they cannot go to larger sizes. The Ha approach solved some of the problems of instability in GSLW, but this scales now cubically with CPU time, and also has this disadvantage of requiring variable precision arithmetic. The optimization approach scales just quadratically, because that comes essentially from the optimization routine, which is basically a gradient approach, standard approach. And we can go up to, so we showed it here, only up to the values which the other groups have calculated to, but we can go up to 10,000 degrees of the polynomial, which has the advantage, it means you can take essentially quite large, very large time steps for the expansion. So we've also done this for different target functions, and this is summarized in this preprint here on the archive. I think I should say a few more words about this, but I won't go into detail here. We found that there's a symmetry property of the phase factors, which is one of the reasons why we get such an efficient solution. We can reduce the number of degrees of freedom of the optimization by only by a factor of 2, but still in a complex landscape, it's quite it's quite an advantage. So we generally use this symmetric construction of phase factors, and that enables us to reduce the effort there. We also find that the phase factors show a characteristic decay. This is a Hamiltonian simulation problem. The magnitude of the phase factors as a function of the distance from the origin of the expansion. This is the second problem we've looked at, quantum eigenfiltering problem and a quantum linear system problem, the inversion problem here, and the decay of the phase factors from the center. So that's well understood. And so to summarize on this part of the talk, we really have now, I think, interesting explicit construction of QSP that can actually start to be used to actually implement the algorithm, at least in small cases. It's an optimization-based algorithm for finding the phase factors, has high error, so in the polynomials less than 10 to the minus 12 for up to 10,000 order polynomials. We do this with standard double precision arithmetic, so it's fairly straightforward to program. There's no reduction, no root finding, only matrix multiplications. And one feature is that because the optimization landscape is very complex, it's important to choose the right initial points. And the symmetry properties help with accelerating the optimization. The next steps here, I think, will be to look at the robustness of this. So we've done some initial work here. One makes an analysis of the Hessian that identifies the points at which the system is sensitive to different phase, to small changes in the phases. And we're starting to look at now applications of QSP on disk machines with this. So that's the first half of the talk, which describes quantum control for help with algorithm design. In the second half, I'm going to switch gears a little bit and focus explicitly on near-term algorithms for NISQ machines, and specifically on the hybrid quantum classical algorithms. So the variational quantum eigensolver is maybe the prototypical example of this. So this is an algorithm for finding energies of quantum systems, and it's been widely applied to the electronic structure problem to find energies of electronic energies of molecules or extended systems. And the idea is that one prepares an initial state, an ansatz, for, say, the ground state of a molecule. And this ansatz would have, ideally, a low-depth quantum circuit representation. So this would be prepared in these quantum modules. And then once these initial states, or the various components of the state are prepared here, and then then there's a measurement made. So the measurement is, in this case, of expectation values of terms that contribute to the energy. So different contributions to the electronic energy are measured. And then this information, these outcomes of these measurements, so this is quantum state preparation and the quantum measurement here. These quantum outputs are now fed into the classical processor, which will add them together and then input those now classical numbers into an optimizer, which will optimize the parameters in the quantum circuits involved here to minimize the objective function, which, if it's electronic structure, would be the ground state. It would be minimizing the energy, electronic energy. And then those new sets of parameters are then fed back into the quantum state preparation. And then this is iterated. So this is a setup where you have a quantum core, a quantum eigensolver here, which is embedded in a classical optimizing wrapper. So there are two major challenges to this that have emerged, I think, as people have studied this quite extensively over the last few years. The first point, which is the reason why the method was developed, is that small noisy devices don't allow for deep circuits because of the restricted coherence times and gate fidelity. So then as a result, one replaces, one does what one can with the restricted coherence times to get as good initial states as one can. But then one requires large numbers of repeated circuit evaluations to make the measurements and then as input for the classical optimization. So these two different challenges of large repeated circuit evaluations and restricted coherence times reflect two different kinds of limitations. One is the coherence time, which limits the quantum part. And the other limitation, which is only really starting to be realized now, is the total wall clock time. And this puts limitations on all hybrid algorithms. And this limitation on the wall clock time includes the, well, I'll say that. Okay, let me say a bit about each of these two limitations now. Firstly, the coherence time limitation. So the limited coherence times of the qubits in the near-term devices imposes an upper limit on how long a single computation will take. So in other words, how long you can actually, how large your circuit can be to make your initial state even. Then the noisy nature of the available quantum gates, that has another limitation on that. And then to quantify this, people generally take the total 2-qubit gate count as a good metric for estimating the coherent costs, because these are mostly the dominant source of infidelity in most near-term devices today. Then, so this is now the second limitation, which is the total time or the wall clock time complexity. So this comes from a number of sources. The one obvious one is that you're executing a large number of relatively simple circuits. So you have to repeat many, many times. So these many times may be indeed quite prohibitive, especially when one tries to go to larger numbers of systems, larger size systems. And there's been some very nice studies of the scaling of this. One here by Wecker, Hastings, and Troyer for specific cases in the electronic structure domain. Then you also have calibration drift and other time-dependent errors, which limit the size of the time window in which you can actually do a real experiment. And that's very important for the people building the devices. We don't normally think about that in designing an algorithm, but it does place a limitation on what you can actually do in practice. So the number of circuit repetitions required is one measure of the cost for present-day systems. And the number of circuit repetitions required will then be also intrinsically an estimate of the number of measurements that are required. So how do we reduce these costs and enable trade-offs between them? So there's three methods that we have, three approaches we've taken at Berkeley in terms of trying to optimize the trade-off between these using for the electronic structure problem. One is reducing the number of 2-qubit gates required by design of new improved Ansätze. So I say a couple of words about that because it's essential for understanding the language, but I won't dwell on this in too much detail. What I want to focus on really is this kind of steps 2 and 3, which are trading 2-qubit gates for circuit repetitions by using a linear combination of Ansatz states, and by then reducing the number of measurements by using a change of basis. So now, next slide. Okay, so we're using basically for electronic structure, we're always using a unitary coupled cluster Ansatz for the states. That derives from this basic equation here, or the classical coupled cluster, which is used routinely in quantum chemistry and for electronic structure calculations. This scales, so this has single and double excitations of electrons from spin orbitals in a molecular wave function. It scales as order 10 to the 6. It's actually not unitary, as you can see here, and so it doesn't evaluate the energy variationally. This can be made unitary. This scales now exponentially, classically, so people don't like to do this on classical computers, and it has order n to the 3 circuit depths for 1 Trotter step. But this is the way you want to go for a quantum computer, because clearly unitaries are, if they're correct, that's the easy thing to implement on a classical computer. So this on a quantum computer is indeed variational. So then the question, though, is you have many, many amplitudes in these trotter, even in a single trotter step. So you have a number of amplitudes, which is determined by the number of spin orbitals in the system and also the number of electrons. And if you have generalized excitations, you get still n to the 4 excitations. So what we have proposed is a reduced form of the coupled cluster, unitary coupled cluster, which has only kn squared amplitudes. So I won't go into detail of this. I just put this down here because we're going to use this later on. So I won't go through this. So I'll just now go to the second point, which is to remove or to replace the normal VQE, which is approximating the ground state with a parameterized quantum circuit, with an Ansatz wave function psi, to replace this now by a linear combination of m parameterized circuits, each one, so k is 1 to capital M here. When m is 1, you've got regular VQE, but now with m greater than 1, we get a generalized eigenvalue equation, which is a well-known equation in electronic structure. But the advantage of this here is that what we need to do is to measure now matrix elements of Hamiltonian between the different states, and also the overlap matrices. And then we can solve the generalized eigenvalue equation classically. And the advantage of this now becomes clear. When we analyze this, we saw that measuring the off-diagonal elements can be done, certainly using unitary coupled cluster states, using the unmodified state preparation circuits for each ansatz, together with only 2n controlled swap gates, and a small cost for coupling to an ancillary qubit. So this cost is independent of the number of states one includes in one's linear combination. That allows us to increase the representational power of the state without requiring more coherent quantum resources. We're still using the same low-depth quantum circuits as we did for a single state VQE. However, now though we have these many matrix elements of order m squared, and that requires overall more circuit evaluations. So what we see here with some results is for hexatriene, that's a molecule with 3 minutes. Okay, so I will go through this quickly. That's a molecule of 6 carbon atoms, and let me just focus on one form of this on the left. Say, for instance, you see that when we take VQE, that's m equals 1, so that's this left x-axis down here. When we have these are the K is the unitary coupled cluster modification that I showed you before. We rapidly reach chemical accuracy here with k equals 1 up here. Gate count increases with k. But if we use NOVQE, we require fewer 2-qubit gates with regular VQE calculations. We take k as greater than 2. So that's the savings. And now the last point is with measurement. So the last point with measurement is that if you divide up the Hamiltonian into a sum of Pauli words, then you can group the terms into simultaneously measuring sets. This usually results in n to the 4 different groups, but you can rotate the terms in your Hamiltonian first with single qubit rotations, relatively easy to implement, and giving essentially a factorization which reduces the number of circuit repetitions for measurement. And the net effect is, if you do this right, you can reduce the number of measurements from n to the 4 to just of order n. And this is a significant reduction. So I will, this is just the results. So I just look here, the hydrogen chain. Here you see that the number of qubits here is the x-axis, and the measurement time is increasing as you increase the number of qubits. But we have three different kinds of making measurements. If you make the usual form of measurements, separate measurements, you increase, you have the greatest amount of measurement time. But if you do this basis rotation followed by a grouping, then the measurement time appears to saturate actually as the number of spin orbitals increases. So this looks promising for going to larger sizes on these machines. So this is now the summary for this part of the talk, the second part. So basically we've looked at these two different resources, the number of 2-qubit gates which can be formed limited by coherence time, and the number of overall circuit evaluations. We've seen several strategies, and particular strategies of modifying the number of measurements and making clever factorizations of the measurements that you need to make can benefit you with a trade-off here. The outlook is, can we reduce both types of costs to affordable levels for significant problems? That's really the real challenge here for the NICS machines. And it will be very important to do this in order to make progress to larger size systems with VQE calculations on NICS machines. So these are some references for the work. This is references just from our group, but there's many others in this area as well. And let me just thank now the people who did the work. So Yulong Dong did in my group, together with Zhang Meng, our student with Professor Lin Lin and Math, did the work on the QS quantum, the control, QAOA and quantum signal processing. And Bill Huggins and Brian O'Gorman from Pilbeck, together with Junho Lee and Martin Hay-Gordon's group at Berkeley, did the work on the electronic structure calculations. And we also benefited from a collaboration with the Google group on the measurement reductions, and the last piece of work I talked about, and also with Nathan Weber from University of Washington. And with that, I'd like to thank DOE and Google and NASA for funding, and I'm happy to answer any questions.
Okay, thank you for a fascinating talk. So normally at this point we thank the speaker, so people seem to be thanking the speaker by clapping in the Slack window where we have the Q&A. So I'll have my own virtual clap to that. So just to remind everyone, please put your questions in the Slack channel. I'll give everyone a moment to put any questions they have now. The claps are all piling up, fantastic. Okay. Start with our first question. So we have a question from Puyo Rongma. Sorry if I got your name wrong there. He says, explain why or in what sense QAOA admits a bang-bang optimal control. So I think you were, in the first part of your talk, you were talking about QAOA.
Yeah, yeah. No, that's a well-known result. It's actually, there's different ways to show it. If you know, I mean, there's a result, there's an approach from control theory called the Pontryagin principle, which show, which is basically about half a page of algebra, and you can show that it alternates. If you have two different controls, then you have to alternate between the maximal values of each of them. There's a reference. I can on Slack. I can give a reference.
Okay.
Post a reference
Can
for
you
that.
say again what the name of the principle is?
Pontryagin.
Pontryagin.
There's a paper from the Google group a few years ago which shows this quite nicely. I can post that reference on Slack.
Okay, that'd be good. Yeah. So I had a question which was, I think when you started introducing the unitary couple cluster, you said that there was some kind of trick you used to cut down the number of excitations that you were counting. So was it, you did all of this and some of the doubles, but not all of them or something? I missed a bit.
Yeah, I know that was going a bit fast at the end. So I'll go back to that slide now, okay?
Okay.
So this one. Okay. Okay, let me go here. Can you see it?
Oh, it's gone to acknowledgement slide now.
Yeah,
I think you're on the right one.
This is very odd. Oh, maybe this is, sorry, I just found the right place to do the, okay, got it, here, got it here. All right, so normally, okay, so let me go back here. Okay, this is the general form, couple cluster with so-called singles and doubles. So when you do an electronic calculation for a molecule, your typical ansatz P would be a single Hartree-Fock determinant. Okay, these are, because you have these are electrons, so you need determinantal states for them to preserve the antisymmetry of the fermions, the electrons. Okay, so if you take a Hartree-Fock, then you consider determinant, then you consider the operator e to the t, the cluster operator, generates excitations from that Hartree-Fock, those Hartree-Fock orbitals. And so the first set of excitations would just be single excitations, where you move an electron from orbital I to orbital A. And then the second set of excitations are so-called doubles. They're shown here, where you're moving two electrons from orbitals I and J to orbitals A and B. Okay, so this is what has this order to the n scaling. And it's even worse if you make the unitary form of this, it becomes exponential scaling. So what people have done in the past is, let's see, okay. This is UCCSD, singles and doubles. All right, so what we're proposing is this k-fold unitary pair with generalized singles and doubles. So generalized singles and doubles means that you can go from any orbital I to any orbital A. No restriction. So what we do, instead of allowing those most general double excitations, we restrict ourselves to those which only move pairs of electrons. So that means here that you would be moving, so the single excitations are still you move a single excitation from P to Q, that's basically as it was before, but the doubles, you move a pair, so this is AP, so you've got P alpha and P beta, those are two different spin orbitals, both on the same atom, P. You move those two together to the orbitals Q alpha, Q beta.
Mm-hmm.
Okay, so that's a restriction, moving pairs. And to make up for that restriction, we allow instead to have k-fold products of each elementary block. So we have one block here, another block here, and another block here. So that allows for, in a sense, having correlated moves of pairs of electrons, correlated in the sense of this construction of the product here. So that's the physics of what's included. And of course, if you were to increase k to, as you increase k further and further, you regenerate more of the original unrestricted doubles, but okay, but they're all correlated, and they're all pairwise moves. It's not completely unconstrained. And then we use a trick using fermionic swap gates to reorder the modes of the system to allow this to be now implemented efficiently essentially in order kn depth with kn squared gates. So here's an
okay,
example.
that's much clearer.
What? Yeah.
That's much clearer now. Thank you.
Yeah. I'm sorry. I was rushing at the end because I knew that the time was running short. So here's an example at the bottom. If you have H4, it's a square molecule. It's not really a real molecule, but it's been used over the years as sort of as a good standard for a problem that can be either easy or hard in quantum chemistry, depending upon the distance between the hydrogen atoms and the geometry of it. So it's a sort of standard place to start as when you're looking at strongly methods for dealing with strongly correlated systems, which is one of the hopes of quantum computing for the electronic structure problem. So in this example here, we've got this four atom molecule described by 8 qubits, and we have basically a circuit with 536 2-qubit gates, which is not unreasonable for implementation today. Okay.
I think we've passed 6 o'clock, but no one's come to kick us out of the room yet. So yeah. I'll just see if there's 1 or 2 more questions, and then okay. So we have a question from Yutaka Shinkano. So he says that on the second part of the talk, he has a question about the accuracy of the UCCSD method compared to CCSD, which you mentioned in the pardon. So his question is, are they the same? He says, is the UCCSD method the same as CCSD?
No, not at all. No, this is actually a good question. They're not at all. So let's back to this first slide here. So yeah, CCSD, I think, is this what you're saying, CCSD?
So what, I think I know what your answer is going to be, but yeah, I think he's asking, I'll read it out again from the beginning, okay, to make sure that I've got it correct. So it says, I have a question on the accuracy of UCCSD method compared to CCSD method, so unitary couple cluster SD with couple cluster SD, which you mentioned in the standard method in quantum chemistry. Is this the same? And then he sends a link to something.
Yeah, they're not the same, and they're not the same because firstly, the CCSD would be this here, classical couple cluster with containing the T only being these singles and doubles. So this is actually not variational because it's not unitary. Whereas if you make it unitary, which you can do by constructing the operator e to the t minus t dagger, this is now a unitary state, unitary operator here, then it does become variational. It becomes more efficient. And if you can do this, this is indeed more accurate than this.
Okay, so I think we should finish up now. So if everyone wants to thank Birgitta again with a virtual clap.